Welcome to the 2021 Photonics Spectra Optics Conference, a showcase of this year's industry innovators along the global optics manufacturing value chain. In this session, we're joined by Dr. Oliver Poost. Poost recently joined Hoya Optics Europe as Director of Sales and Marketing. But before that, he was responsible for global sales and marketing activities at Delta Optical Thin Film for 10 years. He has long-term experience working with international partners and in the sales of high-tech equipment to research and industry customers. In this presentation, he's going to be giving you a technical and market-centric overview of optical filters in 2021. At any point during the talk, you can leave a question or a comment in the chat on your screen. And if we don't respond to you during the conference, we will follow up with you later by email. And if you missed part of the talk, you can come back later and watch it on demand. So that's all from me. I'd like to introduce Dr. Oliver Poost. Welcome.
Thank you so much, Sarah, for the introduction and for the possibility to speak to your audience. My name is Oliver Poost, and I will talk about optical filters. So I welcome everybody to join this presentation. I will talk about technologies and applications and answer the questions, are optical filters a commodity? Having heard about my background, I think you know that this is a rhetoric question and what my answer will be. So in this presentation, I will try to convince you about that optical filters are not a commodity. Here is the content of my presentation. I will tell you what I understand with optical filtering, give a very short overview on the history of optical filters, define the filter types by their functionality, and explain the principles how optical filtering can take place. I will share some market observations with you and then dive into thin film filter production technologies, and in that context cover the choice of substrate for thin film filters, the impact of large angle of incidence, and explain some cost drivers in filter production. And as the last topic, I will show you some applications of colored glass filters. So what is optical filtering? Optical filtering takes place when we talk about that part of the electromagnetic spectrum that deals with ultraviolet to the mid-infrared. And the basic functionality of an optical filter is to transmit one part of the spectrum and to block or reflect another part of the spectrum. And from my point of view, a good optical measurement always starts with a high-performance optical filter. I will share some experience about requests that I received through the years at Delta Optical Thin Film. So believe it or not, I received a request for a coffee filter. It's one of the most used filters, but definitely not an optical filter. Once in a while, I received requests for mechanical filters. Also, these are important, but again, not our topic. And more often, I received requests for electrical or electronic filters. While these are certainly very interesting, we do not want to talk about them. So here we have the optical filters in different shapes and functionalities, and that is what we want to talk about. But you already see when you receive these spurious requests, there are some people who consider filters a commodity, and so you can end up with something that is not really what you deal with. The history of optical filters or optical filtering goes back more than 2,500 years to ancient Egypt, when the Egyptians already knew how to stain glass to make it colorful. Of course, it was not used in instruments, but for decorative purposes. And then we make a big jump to the last century when Walter Gefgen, first in Jena and later in Mainz, invented thin film interference filters and got his patents in the 30s and 40s of last century. These were then based on interference on thin films, where you can see an example on the right-hand side of the soap bubble that uses the same effect. The filter types by their functionality can be divided into shortwave pass filters. These transmit the shorter wavelengths of the spectrum, while they block the longer wavelengths. When you are an electrical engineer, you know them as high-pass frequency filters. Then we have the opposite, long-wave pass filters, that transmits the longer wavelengths and blocks the shorter wavelengths. Again, electrical engineer use a different terminology. low pass frequency filter. And then we have band pass filters that transmit a more or less narrow band of the spectrum while blocking the shorter and the longer wavelengths. The opposite of that would be a notch filter or band stop filter that blocks a narrow band while transmitting the shorter and the longer wavelengths. And then we have what people often call dichroic filters. These are available as shortwave pass filters and as long wave pass filters again. So they transmit either the shorter wavelengths and reflect the longer wavelengths, or transmit the longer wavelengths and reflect the shorter wavelengths. Very often they are optimized for an angle of incidence of 45 degrees and are used as dichroic beam splitters. So in these filters, the complete wavelength range is used, and no part of the wavelength range is blocked out. I also want to mention a special type of filters. They are only available as thin film filters. These are continuously variable filters where the wavelength characteristic changes continuously along the length of the filter, which is achieved by a coating that varies continuously in thickness along one dimension of the filter. Why is that interesting? You can replace any number of discrete filters with just two continuously variable filters. You can achieve unlimited tunability over several hundred nanometer wavelength range. You can create wide bands and narrow bands and independently tune center wavelength and bandwidth. And in an instrument that needs to be flexible and tunable, it reduces complexity and cost and space requirements. On the right-hand side, you can see for comparison how that is traditionally solved with the filter wheel that has some limitations compared to the elegant solution with continuously variable filters. There are several ways of how you can achieve optical filtering. The basically oldest, going back to ancient Egypt, is colored glass filters. We talked about that. They work by absorption. You stain an optical glass with different materials that have different absorption characteristics. Then you have the more recent thin film filters that, based on the effect of constructive and destructive interference. There's another technology that is used for mass-produced color filter arrays in every color camera. These are inorganic pigments or organic dyes on a plastic substrate. And you can use liquid crystal filters. They are based on the principle of biorefringence in the liquid crystals. And the last option is to use acousto-optic filters. They are based on diffraction, which again is based on photoelasticity effect when a radio frequency source induces density variations in an optical crystal. But today we only want to talk about the first two types of filters, which are most widely used: colored glass filters and thin film filters. So what is the difference? What are the characteristics between colored glass filters and thin film filters? The first type, as mentioned, is based on absorption. So the blocking is based on absorption, which has the nice effect that all the light that you do not want to have in your instrument, that you do want to block, is absorbed in the filter, and that reduces the stray light level quite a lot in your instrument. The downside is that you have limited choices of the wavelengths because you have the chemical elements that are available in the periodic system. You can't design every filter functionality, but you still have a reasonable choice of wavelengths. And one of the major benefits is that this absorption effect is not sensitive to angle of incidence. So the filters do not have any angular sensitivity. I will come back to that later. They have moderate environmentally stability, but on the other hand, when you have scratches on colored filters, these scratches here are merely cosmetic. Thin film filters are based on interference, and if you want to block the wavelength range, it's done by constructive interference. But that means that all the undesired light in your instruments will be reflected back into the instrument and needs to be handled, dumped somewhere. You definitely need to care much more about stray light with thin film filters. An advantage is that they can, in theory, be freely designed. Not everything can be produced, but you can design every filter functionality that you can imagine. but it comes at the price of a very high angular sensitivity. Again, an advantage is they have with modern production technology high environmentally stability, but because these are thin films on glass substrates, the scratches that you might have on a filter will degrade their spectral performance. So what is also possible is that you coat the filters on colored glass, and that can be, for many applications, an ideal combination of both benefits from both worlds. I will also mention that later. Yeah, some market observations that are made through the past years since I deal with optical filters. So what I observed is that the market experiences a polarization, like many societies, if you will. So the middle class drops out, and the same is true for the filter technology. So there's one application where you need inexpensive standard filters for high volume applications. You can see an example where you have limited transmission, and also the blocking is not as deep as it could be, and the wavelength range is not very big, and the edges are not very steep. And on the other hand, you have very complex filters for high-end applications, which of course have a higher price, but they are then suited for the most demanding applications nowadays, with very high transmission levels, very steep edges, and a very deep blocking over an extended wavelength range. So there's not much room left for what has for several years been the standard filter types. Some more observations. You can see that in many customer contacts, the filters are often overlooked, but in fact they are a crucial component of optical instruments, because if you think about it, if an optic instrument needs to take a measurement, it always starts with the optical filter in the path of the light. So they need to be definitely considered. I also saw that the customer contact happens later and later in the development process, because people first design the instrument and then inform themselves about optic filters on the internet, and only come to you at a late stage when the instrument is more or less ready. And then it often turns out that a filter cannot be designed, or it can only be produced at prohibitive cost, and that should be avoided. I also see that there are more and more companies that do not really have optical specialist knowledge themselves. For example, in small startups or companies dealing with LiDAR. And then mechanical or electrical engineers are tasked with the optics, and that also can make things difficult. For example, you really have to make sure that you use the same terminology or understand the same with the words that the parts use in the discussion. Another hint that filters are considered a commodity by some companies is that requests for quotations come through purchasing, and that the access to the technical staff is very limited or restricted for internal reasons. And that can be then challenging to propose a solution that is both application specific and cost effective at the same time, if you cannot discuss about technical specifications with the engineers in the background. Yeah, I mentioned that I want to go through some of the filter production technologies for thin film filters. In the early years of thin film filter production, last century, the soft coatings were used, and they are made from zinc sulfide and cryolite, and often contain thin metal layers like silver. And very often they are glued together from many substrates to achieve the overall filter performance. They typically have poor environmental durability and poor temperature stability. The transmission and blocking levels that are achievable are quite low. Because of the many optical surfaces, you might experience high optical scatter. On the positive side is that you have low production cost and low bending of the substrates. So it's still an option that you have in the market. They are offered, and sometimes it's not quite clear that these are soft coatings, so you need to make sure what type of production technology your filter manufacturer uses. Then later, the traditional hard coatings came into existence. They are produced with a plasma-assisted vacuum deposition process with metal oxides. Modern equipment is computer controlled, and you can deposit a higher number of layers for more complexity of the filter functionality. They are also environmentally more stable, but still may contain some voids that absorb water vapor. And with the water vapor, the refractive index changes, and so will your spectral shift occur. So you also need to consider that when looking at filters nowadays. And the most modern filters since 10, 15 years are what I would call ultra hard coatings. They are produced with IBS or ion beam sputtering, magnetron sputtering, or APS processes that generate very dense and amorphous coatings. These have a very high durability and stability. No protection is needed for these filters. And you can produce very complex filter designs with several hundred layers nowadays. So we have recently seen advanced filters with 300 layers on each side, which was not possible just several years ago. But also that comes at a cost. The high energy plasma or ion beam induces mechanical stress in the coating, which leads to bending of the substrates. And the thinner the substrate becomes, the more severe the bending is. Another thing to consider is that although these filters have a higher cost, so for the customer, an initially higher investment, you still might see that the cost of ownership is reduced because these filters last longer and do not lead to any degradation over time and a bad customer experience. The more complex the filters become, the more important the choice of the substrate becomes for the quality of the filters. For many, many years, the standard, and still is, are mechanically polished glasses. They can be BK7 or equivalent of used silica or many other glasses. The advantage is that you can have them in virtually any thickness. But you might see that it's not always possible to remove all the polishing residuals, which can create a problem for the growth of the thin film layers on the substrates. And of course, companies try to optimize production time, so they tend to use high-speed polishing, which might induce micro cracks in the surface, which again is not very good for the growth of the thin film layers. So in the recent years, filter companies looked at fire polished glass or float glass like D263, B270 or borough float glass. There are no polishing residuals necessary, or they do not occur. They have a very smooth surface for good growth and uniform growth of the thin film layers. A drawback is that, for example, D263 is only available in 1.1 millimeter thickness as a maximum. And as I explained, these modern coatings, the thicker they become, the more stress they induce. So people are looking for alternatives, which could be borough float, which you can get at 1 inch maximum. But you have to consider that due to the production process as a float glass, the one side of the substrate is in contact with liquid tin. And again, polishing might be necessary to remove that tin. One possible solution that Hoya can offer is high precision polished glass. The advantage is that it can be polished from virtually any of the known materials, and the surface quality, the surface roughness can even be better than that of float glass D263 T Eco, as you can see in the two plots. On the left-hand side, we have the fire polished glass, and on the right-hand side, we have the high precision polished glass substrate. And here the advantage again is that you can have the surface quality of fire polished glass with the thickness of any standard material, which can be larger as 1.1 millimeter to avoid the bending of the substrates. Yeah, thin film interference filters have a natural property, that is the sensitivity to angle of incidence, because if you do not have your nominal angle, the spectral properties will shift towards shorter wavelengths because the path length of the optical ray changes in the filter. So you can see on the left-hand side a plot for 0, 10, 30, and 45 degree angle of incidence. And from the formula below, you can see that the blue shift is a progressive effect that really becomes severe beyond 10 degrees. For example, at 10 degrees, you only have 2 nanometer shift, but at 45 degree, you already have a 40 nanometer shift. The shift itself depends on the material. It is tied to the effective refractive index, and it also depends on the polarization. You can see that for large angles of incidence, the P and S pole have different blue shifts. This polarization splitting has some severe effects especially for bandpass filters. And again, you can see it's for 0 and 10 degrees, it's not really that bad. But for 30 and 45 degree, the transmission drops rapidly, even more for 45 degree, and the bandwidth changes as well. What is not shown in these plots is that also the blocking can be impacted. You see a reduced blocking and sometimes spikes in the blocking area. So angle of incidence is something to seriously consider for thin film filters. For laboratory instruments that are big, like a fluorescence microscope, the situation typically is that you have well collimated light with small cone half angles. You have a dichroic beam splitter that aids with the blocking. And when you use the microscope for observation with the human eye, you only need a limited blocking wavelength range, and the whole instrument is designed for a low stray light level. What we recently see is that the same fluorescence technology is used in smaller instruments, point of care devices. That has been especially fueled by the corona pandemic for corona quick testing instruments. And in these miniaturized compact instruments, you have large cone half angles. You can't use a dichroic beam splitter. And because you have a silicon-based detector, you need an extended wavelength range. And because the beam splitter is missing a higher OD value in the excitation and emission filters. And because of the compact design, it's not very easy to control the stray light level. So that is definitely much more challenging to make good filters for very compact instruments. I found a very nice example in laser focus world that shows the problem. In the left graphic, you see how filter that is a combination of a coating and a color glass has a very crisp signal to background ratio. And in the middle image, you see how that what happens if you replace such a filter with a simple traditional thin film interference filter, and all the light that is now not anymore absorbed in the filter is reflected back in the instrument and creates a high background ratio. So on the right hand side, you see that if you really carefully design an interference filter for high angles, it gets somewhat better, but the best solution might actually be a combination of colored glass and interference filter. I also want to make you aware of the most important cost drivers in thin film filter production. Most important is the blocking level measured with the OD value and the blocking wavelength range. It's very easy. When you want to have higher and wider blocking, you need more coating layers. That takes more time, and longer coating time means a higher price. But also tolerances influence the unit price, because with very tight tolerances, the batch size, the theoretical batch size of a coating chamber can be reduced quite a lot, which makes the yield lower and leads to a higher unit price. And then I have a pledge or an advice to you. Please specify your tolerances in % of the center wavelength or bandwidth. Do not give absolute values, because when you look at ±2 nanometer at 400 nanometer, that is much easier to achieve than ±2 nanometer at 800 nanometers. So if you design your instruments for a certain tolerance at a certain wavelength, express that as a percentage of that wavelength. So it's much easier to fulfill that than for the complete wavelength range. Also, very strict visual specifications can incur higher costs because the yield will be lower. There's no such thing as a flawless filter. And one thing I also recommend is to specify your visual specifications according to the ISO standard and not to the somewhat outdated scratch and dig standard, because scratch and dig is a subjective comparison with a reference standard, and different people might come to different results, while ISO standard measurements are measurements with an instrument that can easily be compared across different vendors and companies. And last but not least, do not over-specify your optical filter because you want to have some safety margin. Please leave that to the filter manufacturer because he needs to take care of that in his production process anyway. And if both of you put safety margin on it, these filters will be unnecessarily complex and expensive. As the last topic, I want to mention some typical applications and advantages applications for colored glass filters. In consumer optics, they are very often used as heat absorption filters or heat protection filters, like in copying machines or projectors. In any still or video camera, you find colored glass filters to match the sensitivity of the sensor to the human eye response. And a very known application is colored glass filters as IR cut filter to remove the IR from the sensor to give the correct color impression. In industrial equipment, it's used for airport lighting, for many sensor applications, for example, barcode readers. So typically applications where the angular insensitivity is important, advantages like for airport display applications to have the right color value. And there are many applications where you want to have UV, for example, banknote identification, fingerprint detection, or UV excitation for creating visible luminescence. And as you might know, that it's very difficult to get thin film interference filters below 300 nanometer. And there are some filters with colored glasses that can achieve that. And again, IR cut filters are a standard application for these types of filters. They are also found in medical and biotech applications, mostly for surgical lighting to give the correct color impression to the surgeon, dental lighting for sterilization equipment with UV light sources, hair removal instruments very often use colored glass filters, decreasing popularity in fluorescence microscopy. Then we have applications in the field of safety, laser safety, for example, where you find laser protection goggles or larger windows in cabins and curtains. And here, again, it's very important that you do not have any angular sensitivity, because if you have a laser beam at an angle, it might just go through in thin film interference filter, and that cannot happen with the colored glass filter. So here it's very advantageous to use colored glass over thin film filters. Then we have a large area of automotive applications. When cars become more intelligent, they use more and more optical sensors, like for LiDAR or artificial intelligence-based cameras. Very often these work with infrared radiation and have very large angles of incidence and opening angles. And here, infrared filters that are based on colored glass are very helpful in the design. One of these filters is a colored glass called RM100, and it can achieve very high transmission, 95% if you apply double-sided AR to it. It has very deep locking in the complete visible wavelength range, and that makes that filter totally unreflective and get a very deep color appearance, which also is very nice compared to thin film interference filters that would create reflections or stray light in the visible. I mentioned that UV filters are very interesting in many applications, and for applications below 300 nanometer, colored glass can be a good choice because their colored glass filters that can have high transmission starting at 254 nanometer, going up to 365. And modern types of colored glass have very little solarization, and they of course nowadays comply with the RoHS directives. They have no lead, no cadmium or arsenic included. So to summarize my presentation, filters are complex, high-performance optical components. So I hope I could convince you that there are no commodities. There are different technologies available for optical filtering, colored glass filters, thin film interference filters, and often a combination of these two technologies is advantageous. Filter are most often a very crucial component in an optical instrument. So be aware of that. Start to think about optical filters from the beginning. Consider them at an early design stage. And one more recommendation, be as open as possible with your filter vendor. He might really be able to help you more than you think if you share details about your application with him. And of course, every filter manufacturer will be willing to sign an NDA with you. And again, last not least, do not over-specify your filters. That's the task of your filter manufacturer, not over-specifying, but making sure the filters meet your specifications. So that brings me to the end of my talk. Thank you very much for your attention. And I will also be available for a Q&A session after the presentation has ended. Thanks very much again, and back to Sarah.
Thank you very much, Oliver. I do have a couple of questions to ask you before we close. And again, to everybody in the audience, if you haven't already, feel free to type a question for Oliver into the chat. So my first question is, what is the single biggest mistake that customers make in the development process of a new instrument from your perspective?
Yeah, from all my experience as a filter supplier, the single big mistake, if you avoid that, it will avoid any other mistake, is really to contact the filter manufacturer at a late stage. So very often it happens when the prototype needs to be built, only to find out that the filter is not possible to design or very prohibitive with its cost. So the earlier you involve your filter manufacturer, the easier it is to design a filter and give you hints how to maybe change the specification and the design a little bit to achieve what you need to achieve in a cost-efficient way. So talk to your filter manufacturer as early as possible.
All right, thank you. I've got one more question. The presentation mentions both thin film filters coated on clear optical glass and filters coated on colored glass. What are some of the benefits of a coated colored glass filter?
Yes, I mentioned also that these combination of colored glass with a thin film coating can be a good alternative in certain applications. And what colored glass is very good at is to achieve the blocking without any stray light. And with a thin film interference coating, you can achieve very nice bands, for example. So if you want a high performance bandpass filter, sometimes it might be a good idea to provide the extended blocking with the colored glass and to define the narrow bandpass with a interference coating.
All right, thank you. That's all my questions for now. Thank you for answering those. And thank you everybody in the audience for your questions. If we haven't answered you already, look out for a reply from us later. And thanks for joining us for Optical Filters, a Commodity, Technologies and Applications. This is part of the Photonics Spectra Optics Conference hosted by Photonics Media. Thank you very much again, Dr. Oliver Pust.
Thank you, Sarah, and thank you for listening.